Okay, we are going to discuss the second portion of the Biot-Savart law, which is actually looking at what happens when we get different lengths of wire and what does the magnetic field around them look like so that we can kind of see trends in that. Now I'll warn you, I've seen some good data for the first part of this lab. I've taken some good data. I've seen some good plots so far this year. I have not yet seen good data for the second part, including my own. Funny, because when I took this experiment from an article I got out of a magazine called The Physics Teacher several years ago, and it seems like a good idea. And I had some notes here on it that I found this morning. These are notes that I was going to use to modify the lab the next time I ran it. We did not do those. So we're going to see how it turns out. It's still okay. The first part should work okay, and we'll be able to discuss the stuff regardless. If nothing else, I have the scan of their data that they published, and I do question a little bit exactly how well they, or how many times they had to do it. So what I'd like from you is data like this. You should already have this plotted out. So all of these had a form, something like, remember when I had you calculate this, we found the magnetic field from the wire is equal to the magnetic field from Earth, which we don't really care what the value is, times the tangent of theta, where when we had this aligned, we have the magnetic field from Earth. We turned on the wire, which is also going north-south, but that means that depending on which direction the current is going, either the magnetic field was pointing that way directly above the wire or this way. Doesn't really matter which for our purpose. Let's just say it's pointing that way. Here's the magnetic field from the wire, and then we found, or we measured, this angle theta using the compass. And that led us to this, that the opposite over the adjacent must be equal to tangent of theta. And so since we were interested in the magnetic field from the wire, that must be equal to whatever this constant value from the Earth is times tangent of theta. So here is really the important part for us. Then, after we did that by raising up the compass and measuring how it changed with varying distance from the wire, we plotted that. So here's some of my data, just to show you similar things. So here I had a length of 0.7 meters, and when I plotted it, it had this curve, which was 0.1 times the distance r to the negative 0.788. And when I went down a little, if I did at half a meter and plotted it, I got something similar but not quite the same, 0.09-ish times 1 over r to the negative 0.33. What I'm interested in is the length and what value of the exponent you got. And we're going to compare those as the wire gets longer and shorter. So I've got a couple from the people not in class from earlier today, and I'll get those out as you're getting yours prepared. Okay. And then, as I recall from class, we had about a 0.06. 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6, and we might have had one other one in there in the middle, I think, 0.25 or 0.45 or something, but we'll get that as we go. Didn't flat your curves yet? So who has one of these that they could share the exponent? It should be
0.3 is 0.
0.3 is what?
I don't know, that one's already up there.
Not helpful. All of these are related to, in some way, the magnetic field, what we're trying to find, is proportional to 1 over r to the n, or some constant over r to the n. What I want is this n. So let's all take a few minutes to plot these. I'll pause the video, and then we'll come back and get them. Okay, we've got most of it now. So then the next thing here, from this experiment, is to plot this. And there were a couple small holes, but we have filled those, so no big whoop there. Going to sort this. Yeah, so we didn't have that, that's fine. Guys, shush.
So it's just because you already had it.
Yeah, we already had a couple, and then I have to insert it. So I want to insert this as a chart and see what we get.
Would length be our x-axis?
Length here is the x-axis, yeah.
We should make a scatter plot.
Okay, so yeah, if I add to this.
Are you looking to add a scatter plot?
No, I already did that. Yep, I have to remind myself how to add the, because every different version of Excel is different. Yeah, there we are. I didn't go far enough. I have an older version at home, I have this one. So this is the n value, which is the r raised to this power, so 1 over r for that. Here is the length. And this, for lack of a better name, we'll call the law. And we'll put that in quotation marks because, yeah. This is what we're used to seeing, and that's what I mean. I apologize. I had notes written to try something a little different. Most of your data looked really good. So that's why I don't really understand why it turns into this when, and mine did too, by the way. This is my data. All of my charts looked good starting out. And then when I combined them all, I got this. Here's what is published. So here's a sample. No. You guys had some of this stuff. This is a sample of one wire. So the ratio of the segments, the tangent of the angle, and r on the bottom. And so several of you had pretty nice looking curves here. But then supposedly, when they combine them all, they get this. To review, theirs, ours.
I can see it.
Yeah, no, this is the. So I don't know. Maybe if we had the notes I had made was that try shorter shims so that we can have it closer. Possibly instead of the large wire, which was the first time I used this, but possibly a skinnier wire would be better too. Yeah.
Do you think it might have been because of like kind of how the distance was? So some of us try to compensate, and also there might be too many variables.
Well, what other variables do you mean?
Well, because you have the pipe that's laying down, and then you set up the compass. But you know, some groups, I know my group didn't always check the compass straight up.
Possibly.
So it could be n plus. I know some of the compasses when you just set it down straight, it like does a complete 360, and then it finally finds it.
That's strange.
Yeah.
I'll grant you. Possibly, but again, the data from the first one looks pretty good. If it follows these lines, to me that seems pretty good. The main thing, so what we are hoping to find from this is, let's see, yeah, we didn't even get there. We should have found, and I didn't find this either, so I'm not faulting you at all. It's really more the experiment, so I'll have to do a lot of work and see if this is worth keeping. We should have found values for that n in between 1 and 2, so -1 and -2. And as this gets really, really long, the longer the wire, the closer it gets to 1. So we're asymptotically approaching 1. So that if this is an infinitely long wire, we should have an R equals to 1. So the magnetic field is equal to some constant over R to the 1. If it gets infinitesimally short, it approaches 2. So that'd be 1 over R squared. Again, theirs and ours. We were kind of going from 0 to 1, so it's a little wonky. Mm-hmm.
Do you think, or do you know, is there any like formula that would be able to like calculate it out?
Yes.
Really
I was hoping to use this to find the formula, but instead, after our next lap, we'll just give it to you.
Sweet.
Yeah.
So
we don't need to copy the table or.
no, you should definitely copy the table, and we're gonna put this out because it's interesting stuff regardless. It just didn't work out that well. Even bad, it's like golf and other things that I won't mention because they're not school appropriate. Even when science is like golf and those things, even when you do it wrong, it's still a good time.
Oh my gosh.
She.
Like golf.
Let go. Yeah.
What's up with the random .44? Random one up there.
Perfect. Where?
.44 on the line in meters. Was that supposed to be there?
Yeah, somebody had, I think, the group that did it 6th hour had .44. They just stuck it together and measured where they were.
Yeah, like the red faction where you have to protect the building, but you blow it up anyway.
Yes, that's what he's talking about, Skylar.
Now our next one will be, we have one more lab to look at magnetic fields like this, kind of a similar way. This is called the Slinky solenoid. We're going to try something new from this one because I do have notes on this. Here's the reason why.
I saw that slow motion video on my phone.
That's swell. We're going to see if we can do that one here. I think we made it. So here's the issue. So in the past we've used slinkies. Slinkies are nice. What I want to do in this next lab is say we've talked about solenoids a lot.
There's 2 3s, that's why.
Yeah, 2.3s. But I am interested in finding out how strong is a magnetic field in the center of a solenoid. We did a little bit of that with work with the lab when you were measuring the strength of electromagnet. We can do it a little more precisely with this because we can vary a couple things. This is a conductive coil. So we can change how much current goes through it and measure how that current changes the magnetic field, and it's big enough that we can put our compass right in the middle. So that's nice. We can also measure how densely packed these coils are by how much it's stretched. So a lot of coils should mean a lot stronger magnetic field. So like this would have a fairly strong magnetic field because there are many coils, each carrying current, each adding to the magnetic field going down the center. Whereas if you stretch it out quite far, not so much. Here's what I want to alter with this though. Because the unfortunate part of this is that slinkies are magnetic, which means after time, when you put current through them, they tend to remain magnetic somewhat, and that can throw off our measurements. So what we're actually going to do is we might try and just set it up to play with it since we have some time today. We might also use that as work time. But set it up to see how it's going to work, but then we're going to make our own slinkies, essentially, our own coils out of copper wire. So we're going to take some PVC and wrap the copper around it tightly to get a solenoid that looks a lot like a slinky. It won't be quite as much fun because the copper will be more rigid, being thicker. But it should avoid the problem of magnetizing the ring itself, and that throws off our measurements. So that will be our next lab task. And after that, we'll summarize it all and discuss the at least the results that we hoped to find. And maybe with this next lab, the ones that we actually found. I have had very good success with the slinky solenoid, the magnetized slinkies notwithstanding. Okay, so that will be our task for today, to sort of get that set up so we can roll with it tomorrow.